Hey guys, my name is Jasa. In this video, I'll be providing an introduction to dynamic programming. This video will cover what dynamic programming is, where the theory came from, and 3 ways to approach the technique. So let's just jump right into it. In general, dynamic programming is a technique for solving optimization problems that call for the maximization or minimization of some important variable. The theory of dynamic programming was introduced in the 1950s by American mathematician Richard E. Bellman. He took issue with the excessive amount of information needed to solve a problem by considering every possible solution. If we momentarily re-examine the situation, not as a mathematician but as a practical man, Bellman wrote, we see that this price of excessive dimensionality, a price that occasionally makes even a modern computing machine cringe, arises from a demand for too much information. Bellman goes on to pose the central question of dynamic programming, which is, how much information is actually required to carry out a multi-stage decision process? The IEEE awarded Richard Bellman with the Medal of Honor for his work on dynamic programming, and the technique continues to be used for solving complex problems, such as those presented by the field of artificial intelligence. So with the origins of dynamic programming in mind, let's now move on to discuss the 3 main approaches to the technique. And to best explain these approaches, we'll be taking a look at a classic problem called the traveling salesman problem. Imagine a young entrepreneur who is eager to sling her latest invention. She feels certain that her product will be a hit, so she wants to visit every town in her area to sell it. Problem is, the entrepreneur's only means of travel is a used car that is horribly fuel inefficient. So she wants to minimize the cost of driving to every town while still being able to make it back home. How does she plan her trip? The classical, less flavorful way of describing the traveling salesman problem is this. Given a set of cities and a distance between every pair of cities, the problem is to find the shortest possible route that visits every city exactly once and returns to the starting point. Now, before we take a look at the 3 approaches to dynamic programming, it's important that we first take a moment to discuss something called the optimal substructure of a problem. Legend says that if you say the words, optimal substructure, in a technical interview, the person interviewing you has no choice but to offer you the job. So what do those magic words mean? An optimal substructure is defined to consist of optimal solutions to a problem, solutions which incorporate optimal solutions to related subproblems, which we may solve independently. In other words, the optimal substructure of a problem allows you to break the problem down into its smallest, most easily knowable parts. Returning to the traveling salesman problem, which from now on I'll call the TSP for short, we can identify its optimal substructure by first asking, what is it that we want to maximize or minimize? Our young entrepreneur would like to minimize the cost of traveling to every town. Next, we ask, what's the first decision that we're able to make? Or more formally, given a starting state, what action can you take to transform the problem into another state? The result of that action is a subproblem. Our young entrepreneur has to start by leaving home, so this question is easily answered. Finally, we ask, what can we do after that first decision is made? The answer to this question determines the recursive character of the problem. And it's important to note here that when you're considering this part of the programming process, you must ensure that the subproblems you're identifying are also themselves optimization problems. After the young entrepreneur has left home, she needs information about the cost of traveling to adjacent towns. So the recursive character of the TSP involves the traversal of these different paths, which must end with a return to home. Now that we've covered what an optimal substructure is and how to find it, let's take a look at the first approach to dynamic programming. The first approach really isn't a proper approach at all. Instead, it's precisely what Richard Bellman was critiquing in his original work published in the 50s. You simply use recursion to traverse every path and calculate the least costly route. This approach is called the naive recursive approach because it almost always involves performing redundant calculations. This approach is also sometimes called the brute force approach. Not very dynamic at all. So let's take a look at the other 2 approaches then, known as the top-down and bottom-up approaches. The top-down, or memoization approach, eliminates the
naivete.
of the first approach by keeping track of subproblem solutions you've already calculated as you go through the recursion. In the case of the TSP, you'd be tracking the cost of traversing paths between towns. Importantly, this way of tracking things is very different and more efficient than trying to track whole routes between multiple towns. Remember, this demand of information is exactly what we're trying to avoid with dynamic programming. Instead of starting with recursion, the bottom-up approach begins with the calculation of solutions to the smallest problems. These solutions then get added to a table, and you work up from there. This approach tends to have better constant factors. In the case of the TSP, you'd calculate the cost of traversing individual paths between towns, add these solutions to the table, and then you're able to avoid redundant calculations by using those known costs to calculate values for the rest of the relevant parts of the table. So there you have it, the definition of dynamic programming, a brief history of where the theory came from, and a discussion of the three approaches to the technique. And dynamic programming is just that, a technique. It's not a silver bullet for solving any complex problem. In fact, the traveling salesman problem has never been entirely and thoroughly solved. Dynamic programming allows us to approach solutions that demand less information and are far more efficient than simply investigating all possible solutions. And although I've presented a general structure for setting up a solution to a dynamic programming problem, each problem is distinct and requires some critical thought in order to really understand the information you have at your disposal and how best to use it. So, with that, I hope you found this brief introduction helpful.